Hello, welcome to the lecture 11 of the course Transportation Network Analysis. So, in today's class, we'll start to discuss some solution approaches for solving important optimization problems. Let me first introduce this minimum spanning tree problem. This is also one of the combinatorial optimization problems. So, before we understand what does minimum spanning tree means, let us first understand what a tree means. So, a tree is an undirected graph in which any two nodes are connected by exactly one path. Okay. So, the first important thing is that here we are talking about undirected graph here. What is an undirected graph? A graph where the edges do not have directions. Okay. So, here on the right hand side we have this figure. This is an example of an undirected graph, and here you can see that the edges do not have any directions, and here if you pick any two nodes here, they will be connected by exactly one path. Okay. So, I mean for example, suppose you take a look at this node and this node. So, there is exactly one path which connects them, which is this path. Okay. So, this requirement is important, that there should be exactly one path which connects any pair of nodes. Okay. Now that we have understood what does a tree means, let us now understand what does a spanning tree means. So, spanning tree of an undirected graph is a subgraph that is a tree and that includes all the nodes of the graph. Okay. Okay. So, the first term here is it is a subgraph. So, what does a subgraph means? So, it is subgraph is a subset of the original graph that we have here. Okay. So, for example, consider this network that is shown here. So, here we have 6 nodes and we have 5 red edges and 3 black edges. Okay. So, if we consider this overall graph, a subgraph of that is the one which is shown by this red color. Okay. Now, note that this is not the only subgraph that is possible, there can be many other subgraphs that are possible. Okay. So, subgraph is just one of the subsets of the original graph that we have. Okay. So, the first requirement is that for a spanning tree, the subgraph should be there, which is a tree. Okay. So, let us look at this network here. So, you can see that this is a tree here, because if you pick any pair of nodes, there will be exactly one path which connects them. For example, if you pick this node and this node here, so there is exactly this one path which connects them. Okay. And you can notice that why there are some black edges which are not part of this subgraph. Okay. For example, suppose if this black edge was also in red color. Okay. And in addition to that, we have this subgraph which is already red showing here. So, then that would not be a tree, because then for example, if you look at these two nodes, this one and this one, then there will be two paths which connect them. One is this direct edge here and the other one will be this edge. Okay. So, therefore, this path here. So, therefore, that will not be a tree, that kind of subgraph. Okay. And the other requirement is that first of all, this spanning tree should be a subgraph that is a tree, and the other requirement is that it should include all the nodes of the graph. Okay. So, you can see here that all the 6 nodes here are colored red. So, this subgraph which is shown is a spanning tree, because it is a tree first and it includes all the nodes of the graph. Okay. So, this is the definition of a spanning tree. Now, a minimum spanning tree, or in short also called MS tree, is a spanning tree whose sum of link weights is the least. Okay. So, consider this figure which is shown here. So, now we have different weights which are provided to different links here. So, now we are not looking at any spanning tree, we want to look at that spanning tree that has the least sum of link weights. Okay. So, here the sum of the link weights in this example will be what? It will be 1 plus 1 plus 2 plus 3 plus 2. Okay. So, that value comes out to be 9. So, for this example, this is the minimum spanning tree which is shown in the red, because first of all you can see that it is a spanning tree in the sense that it is a tree here, since there is exactly one path which connects every pair of nodes here, and then all the nodes are included in this spanning tree. So therefore it is spanning the whole graph here, okay. And on top of that, the total weight of these edges is the least here. So you will not be able to find any other spanning tree that has sum of link weights lesser than this case, okay. So we want to find that spanning tree that has the least sum of link weights, okay. Why MST or this minimum spanning tree problem is interesting? Because it has diverse applications. For example, in building roads in rural areas. For instance, suppose there are some houses that are to be constructed in a rural area, and you want to connect different houses in such a way that all of them are connected to each other, in the sense that there is exactly one path which connects each pair of houses, but you want to do that construction of roads that connect these houses in such a way that the total construction cost is minimized, okay. So the total construction cost can be considered as being proportional to the length of the roads that are constructed, and therefore in that situation this minimum spanning tree problem will be applicable there, okay. So now let us look at some algorithms for solving the minimum spanning tree. So this Kruskal's algorithm is one of the most famous algorithms to solve the minimum spanning tree. So let us see how it goes about solving the problem. So it first finds the link that has a least weight and then it colors it. So here in this example we have two candidates for the least weight. One is this link AB and the other is link AC, okay. So since both of them have link weights equal to 1, so both of them are candidates for coloring, and in this case any one of them can be colored, okay. So whenever we get such a tie, any one of the links can be selected and the final solution will still be optimal. So without loss of generality, let us select this link AB. So we have now colored it red, okay. Now what we do is that we find the uncolored link with the least weight that does not close a colored cycle, and then we color this link, okay. So what does this mean here? We want to find that link which is currently black and has the least weight, but one important thing is that once we color that link, we should not be getting a red colored cycle, okay. So out of all the black colored links here, link AC has the least weight which is equal to 1. So if we color it, so then we can see that these two links AB and AC here, they are not forming a cycle here, okay. So our selection of AC is fine, okay. And then we repeat this previous step until all the nodes of the graph are connected to a colored link, okay. So we want to now repeat this second step here. So let us see that among all the links that are colored black in this figure, which link has the least weight? Link AD and link DF are having the least weight, and here whichever link AD or DF you select, if you color them, then we will not be getting a red colored cycle, okay. So any one of these can be selected. Without loss of generality, suppose you have selected link AD, okay. Now after that we will be selecting link DF, because this link has the least weight among all the uncolored links, and by selecting it we do not form a colored cycle. So you can see here that these links that we have selected so far, AB, AC, AD and DF, they are not forming any cycle anywhere, okay. So there is exactly one path which is connecting every pair of nodes here, okay. After that we will be selecting this link DE here, okay, because this has the least weight among all the links that have not been colored so far, and by selecting that link we do not form a colored cycle. So here you can see that we do not have any cycle so far, which is good. Now every node of this network is connected to a colored link. So you can see that every of these 6 nodes is connected to a colored link. So this red colored portion that you obtained is the minimum spanning tree here, Okay. Now, there is an underlying proof which tells that this minimum spanning tree will be produced for any example problem that is given. Okay. This proof is not being discussed here because there is time constraint and it will be out of the scope of this course. But you can understand that a proof is required because this Kruskal's algorithm will give you optimal solution for any example problem that you give. Okay. So, since there can be infinite such examples, so it is not possible to test each one of them and then see whether it gives the optimal or not, and therefore only an underlying proof can guarantee that it will give the optimal solution for every problem that you give. So, it will in fact give the minimum spanning tree for any graph that you give. Okay. So, this Kruskal's algorithm was discovered by Joseph Kruskal, and he had discovered it in 1956, and he had proved that this algorithm in fact gives the minimum spanning tree. Okay. Now, Kruskal's algorithm has polynomial time complexity. So, let us now understand why it has polynomial time complexity. So, this Kruskal's algorithm implements the second step that we saw repeatedly, that is, it selects an uncolored link that has the least weight, but with the selection of that link it should not form a colored cycle. So, let us see how many times that step will be getting executed. It will get executed at most say n minus 1 times, where n is the number of nodes, because we will be stopping whenever we get all the nodes of the graph getting connected to a colored cycle. Okay. And every time when we are selecting a new edge or new link, a new node gets added into the tree that we are forming. Okay. And also in each of that step, since we have to only select a link that has not been colored so far and that has the least weight and it does not form a colored cycle. So, this checking can also be done very efficiently or in polynomial time, because at most we will have to just go through the set of all the edges that are present in the graph. So, if the set of all the edges of the graph is just m, so we will just have to go through that. Okay. So, therefore, this overall algorithm will take polynomial time operations only, and therefore, it has polynomial time complexity, which is very good. Okay. Now, other than this Kruskal's algorithm for solving the minimum spanning tree problem, there is another very important algorithm which is called Prim's algorithm. Okay. So, let us now see what is this Prim's algorithm. So, this algorithm works slightly in a different way. Here, we initialize a tree by arbitrarily choosing a node from the graph. Okay. So, here we can start with any node of the graph that we want to start with. Let us suppose start with this node E here. So, this has been now colored red. Okay. Now, this is the important step of this algorithm. So, we now grow this tree by adding one link at a time, and the way this link should be selected is as follows. We first find the least weight link that connects the tree to a node not currently in the tree. Okay. And then we add this link to the tree. Okay. So, let us look at here. So, now since we are growing a tree and we have currently selected this node E here, the only edges that we can add at this point are either the edge DE or the edge EF. Okay. Because any other edge, if you add it here, then it will not be a tree, because then this node E will not be connected to that link that you add, and this will overall not be a tree here. Okay. So, that is why we only have the options of either selecting link D or link EF. Now, out of these two links, link D has the least weight. Okay. And when you select that link, we will be also adding the node D to this new tree. So, the current tree that only consisted of node E will now also get connected to this new node D here. Okay. Now, after this iteration, now let us look at what are the choices of links that are available for adding. See, you can add this link EF also now, because when you add that, then link this node F will be added to this new tree. Okay. You can also select this link DF, because with that addition, this tree will now again be connected to node F, which is not currently part of this tree. We can also add link CD, because with that addition we will be adding this node C, and it will get connected to this tree which currently consists of nodes D and the edge D. Note that in this course I will be using the terms links and edge interchangeably. Another candidate is we can add this link AD here. So with that selection we will be adding this node A to the tree that we currently have, and the last choice that we have is to add this link BD. Okay. So at this point we have choices of 5 links that we can add. Okay. And with all of these 5 choices, if we add any of these links, we will be still getting a tree, and this new tree will be having an additional node that is not currently part of the tree here. So out of these 5 choices that are available to us, links AD and DF have the least weight. So any one of them can be selected. Without loss of generality, let us select the link DF here. Okay. So in this algorithm we are repeating this step until all the nodes are in the tree. Okay. So at this point we do not have all the nodes in the tree because the nodes A, B and C are yet to be included in this tree. Okay. Now at this point let us look at what are the choices of the links that we can add here. Note that link EF cannot be selected here, because if you add this link EF, then we will not be having a tree anymore. This will be a cycle, because if you pick any 2 pair of nodes here, there will be more than one path which connect them. For example, if you add link EF here, then you can reach the nodes D and E by this edge directly, and also by from D to F and then F to E. Okay, so then it will not be forming a tree. So you cannot now select edge EF here. So EF is not possible, but you can select edge CD, you can select edge AD and edge BD. Okay. So these are the 3 options that are available to us. Out of these, links AD have the least weight, so we will add that. Okay. Now at this point, let us look at what all the choices of links that we have available to us. You can add link CD, because with that addition node C will get connected to the tree and the resultant will still be a tree. You can also add the edge BD, because with that addition you will be getting node B into the new tree and still the overall subgraph will be a tree. You can also add the link AC, because that will connect node C to the existing tree, and you can also add link AB. Okay. So we have these 4 choices available to us at this moment. Out of all of these, links AB and AC have the least weight. So any one of them can be selected. Without loss of generality, let us select link AB. Okay. Now at this point, since node C is yet not part of the tree here, so the choices of links that we have available to us is either to add these link AC or the link CD. Okay. We cannot add link BD here, because then that will form a cycle here. So since link AC has the least weight as compared to the link CD, so we will add that. Okay. So this is the minimum spanning tree that you have got here. So you can see that this solution is the same as what you had got in the previous slide also. Okay. So this Prim's algorithm is also guaranteed to give the optimal solution, or it will give the minimum spanning tree, and this also has an underlying proof behind it which guarantees that for any problem that you give, this algorithm will give you the minimum spanning tree. But since the time is limited, we will not be going through that proof here. Okay. So this Prim's algorithm was discovered separately by multiple scientists in 1950s. Now this Prim's algorithm also has polynomial time complexity. So let us see why is that the case. So what is this Prim's algorithm doing? Every time it is looking for an edge which is having the least weight, and by addition of that edge the existing tree gets connected to a new node. Okay. So let us see how many times that step will be executed. It will be executed at most n-1 times, because there are n nodes here, because we will be stopping at the point where we get n nodes in this tree, and in the first step we already, actually in this case we will be maybe implementing this step n times here, and in every step here we are looking at a neighboring link whose addition will give you a new node that connected to the existing tree, and that can be done in polynomial time because we will be having at most m number of edges. So, it will never exceed that many operations there. So, overall this is also very efficient algorithm because it has polynomial time complexity. And this is one result which comes from the experimental studies, that Prim's algorithm runs faster in practice on dense graph, whereas Kruskal's algorithm runs faster on sparse graphs, and therefore both of these two algorithms have their own practical importance. Okay, and both of these two algorithms are kind of equally popular for solving the minimum spanning tree problem. So you can see that for both of these two algorithms, saying that they have polynomial time complexity is a very important information. The actual amount of operations here, like it is of the order what n to the power 2, 3, that much of a issue as compared to whether this algorithm has polynomial time complexity or not. Okay. So now let us discuss this traveling salesman problem. This traveling salesman problem, we have discussed it a few times before. In the introduction we had just introduced this, and later we had seen the optimization formulation for that. Note that this traveling salesman problem is NP hard. It is unlikely to find the optimal solution for this problem in polynomial time. There are no such algorithms which can find the optimal solution of this problem in polynomial time, which is a major result. And as I had mentioned, that this traveling salesman problem, since it's NP hard, so we cannot find optimal solution for that, but what we can do is that we can focus on finding approximate solutions for it in polynomial time. So this is the best next thing that we can do here. So what we will be doing is that, suppose let us assume that the triangle inequality holds. Okay. Under this assumption, we will be providing an approximation algorithm for this traveling salesman problem. So let us just see what does the triangle inequality means here. So if you have this triangle here, then the triangle inequality says that the weight of the link AB is less than or equal to the sum of the weights of links BC and AC. Okay. So this is the triangle inequality here. So we will be continuing this discussion of the traveling salesman problem in the next class. We will be seeing what is this approximation algorithm is all about. But remember in mind that this approximation algorithm that we will be introducing will be that based on this assumption that the triangle inequality holds. That is, if you provide a graph for which you have to find traveling salesman tour, that is, you have to find a tour that visits all of the nodes and come back to the original node, but does so in the least time or least distance, then those distances or the weights of the links should satisfy the triangle inequality. Okay. So for example, triangle inequality holds, for example, if you take Cartesian distances and so on. Okay. We will be also seeing later that there can be some examples where the triangle inequality may not hold. Okay. So with this, we will end this lecture here. Thank you.